Okay, so next is on to geometric optics chapter. So the focal length of a lens, it's not the diameter, it's not the thickness, the distance from the lens at which incoming parallel rays bend to intersect at a point. Yep, that's the right one. Look at the last one too. The distance from the lens at which all real images are formed. That is not true either. I think both of these are sort of demonstrably untrue. The other one that you could reason through if you were thinking about C or D is that our typical ray diagram for any lens has the rule that rays that come incoming, and there will be a focal point of the lens. If it comes in parallel to the principal axis of the lens, it bends and goes out through the focal point. So this here, the distance at which incoming parallel rays bend to intersect at a point will be the focal length of the lens. So if you imagine this not being a single object, but a whole bunch of parallel rays that are incoming, all of them come in parallel, bend at the focal point, come in parallel, bend at the focal point, and go out like that. And they'll all cross right there. Next one, suppose you're standing 3 meters in front of a mirror. You can see yourself just from the top of your head to your waist, where the bottom of the mirror cuts off the rest of your image. If you walk one step closer to the mirror, I encourage you to try this, but you will actually be able to see exactly the same amount of your image. So we had this as a misconceptual question. So I think you tend to think that as you get closer, you should see less of yourself. But actually, that's not what happens. So the image of yourself gets larger as you approach that image, but also the angle that things are hitting the angle at, so the sort of the incoming angle and the outgoing angle, also gets bigger. So those two things, the bigger image and the bigger angle, cancel each other out. So we'll see how good I am at drawing this, but if you can imagine being, the best way to mess this up is to try to draw it big. Try to draw it small. So here's you looking at yourself in the mirror, and you have draw this so that the mirror looks just like that. So here you have a ray coming from your eye that would kind of bounce right back and do that. And then you have a ray coming from your eye or a ray coming from your foot that hits right here at the bottom of the mirror, and it will reflect with exactly the same angle. So those two angles will be the same, and it will come and it'll hit you in your eye. So you'll be able to see a ray that comes from your eye bouncing right back to you. You'll also be able to see a ray that comes from your foot, and both of those rays will go in and hit you in your eye. If you now move closer to the mirror, so here you are, and now the mirror is right here instead, you're again still going to be able to see the ray that comes from here and goes back. That will hit there. Draw the mirror. That length and that length should be the same. I'm only making it closer. Now that ray that comes from your foot and hits the bottom of the mirror will reflect, and that angle there should equal that angle there. And these two things, these two angles are the same, so that ray from your foot can still come and hit your eye. So as you get closer and closer to the mirror, you actually still see the same fraction of your body. You just get bigger and bigger. So that the bigness of the image is canceled out by the fact that this angle here, the angle of reflection, keeps getting bigger and bigger. Next is a question about mirrors. So we have a negative magnification for a mirror. So we're looking at mirrors and negative magnification. Negative magnification means it's upside down, so I'm not even going to bother reading the ones that say upright. I'll cross those off. So we have that the image is inverted. That's A, C, or E. The mirror is either convex, the mirror is concave, or we can't tell. So let's draw some ray diagrams. Certainly if you've just memorized what goes with what, then you don't have to think about this, but you can also reason this out pretty good. So the convex mirror, this is the back of the spoon. The concave mirror, that's the inside of the spoon. So vex is something, so when the rays come in, it'll look like that. Rays come in and they bounce off. So for a convex mirror, we will go ahead and make something up. So there's the focal point and the focal point, and there is the object. We'll have in parallel and out through F, and it's actually going to go out through F in that sort of a way. And then in through F, then we'll go in through the principal axis and bounces off in that sort of a way. In some ways, ray diagrams for mirrors are easier because you can kind of use the fact that you know that that angle and that angle have to be equal, that angle and that angle have to be equal, to help you kind of figure out which F you're going for. And certainly if we trace these two back to a spot, that's going to be an upright and smaller object. It actually turns out in looking in the back of a mirror, or these are also like those security mirrors at the 7-Eleven look like this. This is always going to be the case, whether or not your object is inside or outside of the focal point. You will always have an upright and smaller image from a convex mirror, just like you always have an upright and smaller image from a diverging lens. Those are kind of analogous to each other. So it's actually impossible to have a convex mirror that is giving you an inverted image. It always gives you a virtual image, it's always upright, and it's always smaller. So that one is wrong, which means that we're only left with C. But let's check C just to make sure that works. And so a concave mirror looks like that. If we're going to have the inverted images for single mirrors and lenses are always real. So we know that we expect the object to be outside of the focal point because you only ever get real images for objects that are outside of the focal point. Objects inside of the focal point for any real mirror or lens are always going to be real and upright, if the object is inside of the focal point for any mirror or any single lens, then the image will always be real and upright. You'll never, gosh, I said it wrong again. The image will always be virtual and upright. It will never be real. Okay, so for this one, we're going to have in through the center, out that way, reflecting at the same angle. Then we'll also have in through F and out parallel. And so we're sort of seeing that that's where they're going to converge. We'll try in parallel and out through F. Yuck. This is a really bad version of a ray diagram. I think I drew this angle as being pretty big compared to that. I should be drawing it more like that. Now those two angles look more similar, and we're more likely to see them actually cross. So there's a real, because the rays actually cross, an inverted image coming from a concave mirror. So image is inverted, the mirror is concave. That works. The answer is C.